Welcome to this explainer. Okay, if you've ever found yourself wondering how the intelligent robots of tomorrow are actually being built today, you are in exactly the right place. Today we're walking through a complete, beginner-friendly guide to literally the biggest shift in robotics software history. We're talking about the massive transition from ROS 1 to ROS 2. Now, whether you're a student, a weekend hobbyist, or an engineer who's heard all the buzz but maybe doesn't have a deep background in robotics programming, don't worry. We are going to break this whole thing down clearly, simply, and step by step. Let's get right into it. I want to start right here with this specific year, 2025, because it really marks the end of an era. In May of 2025, ROS 1 officially reached its end of life. Think about that for a second. After 18 incredibly successful years of powering university research robots, prototype drones, and thousands of lab experiments all over the world, its time is officially up. There will be no more security patches, no more system updates. It's done. But here is the absolutely critical thing you need to take away from this. ROS 2 isn't just ROS 1 with a quick version bump. It's not just a software update. It is a complete, ground-up redesign. And if you have any ambition whatsoever to build robots that actually function out there in the real world, whether that's a robot navigating a busy hospital corridor, assembling complex parts in a factory, or driving autonomously down a fast-moving highway, understanding the difference between these two systems is absolutely essential. Okay, let's dive into this. Section 1. What is ROS anyway? Moving beyond the lab.
First things first, despite the name, the Robot Operating System, or ROS, is not actually a traditional operating system like Windows, macOS, or Linux. Instead, it's what computer scientists call a middleware framework. You can think of middleware as sort of a hidden translator and delivery service. It's a layer of software that sits perfectly between the physical robot hardware, the actual sensors and the spinning motors, and the higher-level application code that you write to make that robot smart. It provides all the tools, all the libraries, and all the complicated communication plumbing so that you don't have to reinvent the wheel every single time you want to build a new robot. It handles the messy stuff for you.
Now, the absolute core concept of ROS relies on something called nodes. Think about it. A robot is a highly complex machine, right? You've got cameras, you've got wheel motors, laser scanners, and path planning algorithms all running at once. Well, RLS lets all these different parts of a robot communicate as independent software modules, and these modules are the nodes. You might have one node that focuses strictly on capturing images from a camera. You might have another node that just runs an object detection algorithm on those images, and maybe a third node that simply tells the wheels to spin based on what was detected. Each node focuses entirely, 100% on its own specific job, and ROS just magically handles all the complicated communication between them. If that all sounds a little bit abstract, no worries. Let's just think of nodes like the independent apps on your smartphone. Your Maps app doesn't need to know how the camera app works internally, right? Each app just does its own job. The phone's operating system lets them share data, like passing a cool photo over to a messaging app, without each app needing custom code for every single phone model out there. That hardware abstraction is exactly why ROS became so incredibly dominant. It was originally released way back in 2007 by Willow Garage, and it quickly grew to include thousands of ready-made code packages. Because it was open source and had a massive academic community behind it, you could write your code once and run it on everything from a little classroom turtlebot to a massive NASA rover. It was a total game changer. Moving right along to Section 2, how ROS 1 works and the core architecture. All right, so in ROS 1, how do these nodes actually talk to each other? Well, there are 3 core communication primitives. You have topics, which are continuous data streams. You have services, which are used for quick request and response actions, and you have parameters for shared configuration settings. But sticking to topics for just a second, let's say a camera node publishes a continuous stream of images to a topic, and an obstacle detection node subscribes to that same topic to receive those images. But here's the catch. They can't just blindly shout into the void. They have to find each other first. So the process looks like this. Step 1, a node starts up. Step 2, it registers itself. And step 3, the nodes finally connect directly to one another. But where exactly do they go to register? They register with something called the ROS Master. The ROS Master is essentially the central brain of the entire ROS 1 network. It acts as a central registry that maintains a highly detailed directory of exactly who is publishing data and exactly who wants to subscribe to that data. I really cannot overstate this point. Every single node must register with the master on startup in order to find other nodes. If a node doesn't check in with the master, it's completely invisible to the rest of the robot. The absolute best way to visualize the ROS master is like an old-school telephone directory, or maybe a switchboard operator. If node A wants to talk to node B, it calls the directory to get node B's address. Once it gets that address, node A calls node B directly. The directory itself doesn't stay on the line, it doesn't listen to your conversation, and it certainly doesn't handle the actual massive data streams of 4K video or dense laser scans. It just makes the initial introduction. To pull this off, the original ROS team built their own custom TCP and UDP-based communication protocols from scratch, known as TCP-ROS and UDP-ROS. And all of this code was organized into packages using a system called the Catkin build system, running pretty much exclusively on Linux, specifically Ubuntu.
Which brings us to Section 3, the 5 big problems with ROS 1, and honestly, why it had to die.
Look, that central architecture we just talked about, it was totally brilliant for academic research back in 2007. But as robots rapidly evolved from basic lab experiments to actual commercial products, some major cracks started to show. There are 5 critical, fundamental flaws with ROS 1 that made it completely unsuitable for modern, high-stakes commercial deployment. It basically boils down to this: a single point of failure, a total lack of real-time guarantees, absolutely zero security, being completely locked to a single operating system, and having no way to safely manage the life cycle of the hardware. Let's break these down one by one because this is fascinating. Now, what's really interesting about this first problem is the ROS master itself. Because every single node relies on the master to connect, it creates a massive single point of failure. Picture this. In a university lab, if the ROS master crashes while a prototype robot is wandering the halls, it's annoying. You just reboot the system and grab a coffee. But imagine a robotic arm performing delicate surgery, or an autonomous vehicle driving at highway speeds. If that central registry crashes in those scenarios, the entire robot system loses coordination. No new connections can be made whatsoever. For safety-critical systems, that isn't just an inconvenience, that is an unacceptable, catastrophic failure. ROS 1 was designed for controlled lab environments, pure and simple, not production deployment. So, the crucial point for problem number 2 is real-time support. Or rather, the total lack of it. In computing, real-time doesn't just mean really fast. It means deterministic. It means mathematically guaranteeing that a message will be delivered within a strict, non-negotiable deadline. If a research robot is just mapping a room, a few milliseconds of delay, what we call jitter, is perfectly fine, no big deal. But for a flying drone trying to stabilize its rotors 400 times a second, or an autonomous car that needs to trigger the emergency brakes the exact millisecond a pedestrian steps out, you need bounded, deterministic latency. ROS 1 simply cannot guarantee when a message will be delivered. It literally cannot promise that the brake command will arrive on time. And that's a deal breaker.
Problem number 3 is honestly kind of terrifying in a modern context. ROS 1 has absolutely zero security. I mean, none. Zero. There is no authentication and there is no encryption. Nodes just communicate openly on the network. Any device connected to the same network can intercept messages, or infinitely worse, inject false commands or block signals entirely. Now, in a private, lockdown academic lab network, sure, that's an acceptable risk. But if you deploy a fleet of medical delivery robots in a real hospital using the public building Wi-Fi, or industrial manipulators on a busy corporate factory floor, ROS 1 leaves them completely exposed to hackers. It's totally unacceptable for commercial use.
And finally, we have problems 4 and 5. ROS 1 is heavily locked into Linux, specifically Ubuntu. No Windows, no Mac OS. It also inherently assumes you're only working with a single robot. Getting a distributed system or a swarm of robots talk to each other requires incredibly complex, messy workarounds. On top of that, there is zero lifecycle management. In ROS 1, as soon as a node starts up, boom, it immediately becomes active. It's ready to send and receive commands instantly. That means a giant industrial motor controller might start accepting movement commands before the robot's safety sensors have even finished booting up and calibrating. There is just no safe, standardized way to wake the robot up gracefully.
All right, let's turn the page to Section 4, the ROS 2 breakthrough, entering the real world. So the developers knew they had a massive problem on their hands. Recognizing these fatal flaws, they made a really bold choice around 2014. They didn't try to just bandage up ROS 1 with a few patches. Instead, they initiated a massive, ground-up architectural overhaul to build a system that could actually survive and thrive outside the lab. Enter ROS 2. The single most important decision the team made was throwing out their custom-built TCP-ROS and UDP-ROS communication stacks. They tossed them entirely. Instead, they built ROS 2 on top of an existing, hugely successful standard called DDS, or Data Distribution Service.
What is DDS? Well, it's an open international standard for real-time, reliable, and secure peer-to-peer data distribution. And here's the best part. It wasn't invented by robotics researchers. Long before ROS-2 existed, DDS was already the battle-tested backbone for military battleships, space satellites, air traffic control systems, and complex financial trading platforms. It is serious, industrial-grade technology.
And this brilliantly illustrates how DDS completely changes the game. Remember that telephone directory analogy with the ROS Master? Well, DDS is completely decentralized. It is truly peer-to-peer. Imagine a neighborhood where instead of having a central directory, everyone simply puts a sign out on their front lawn saying exactly what they offer, like, hey, I sell apples, or I need a plumber. If you need apples, you just walk directly to the house with the sign. There is no central directory required whatsoever. Through a distributed discovery protocol, the nodes automatically find each other on the network. If one node crashes or one house is totally removed from the neighborhood, the rest of the system just keeps functioning perfectly. The single point of failure is completely gone.
Okay, but what about that terrifying security issue we talked about? Well, ROS2 tackles security head-on using the DDS security plugin. Now, nodes actually have to use X509 certificate authentication just to prove their identity, meaning rogue, unknown devices simply cannot join the network, period. Plus, all the data traveling between nodes is fully encrypted in transit, so nobody can snoop on your robot's private sensor data. And it features really strict access control policies, dictating exactly which nodes are actually allowed to publish or subscribe to specific topics. Because of all this, ROS2 robots can safely operate on big corporate networks, use public Wi-Fi, and successfully pass rigorous enterprise IT audits. It's night and day compared to ROS1. ROS2 also brings in a massive safety feature: lifecycle nodes. Instead of hardware just waking up and wildly accepting movement commands right off the bat, ROS2 creates a strictly defined state machine. A node starts its life as unconfigured. Then it carefully moves to inactive, which is where the hardware initializes. The sensors calibrate, the encoders get ready, but it still won't move an inch. Only when the overall system confirms everything is 100% safe does the node transition to active, where it finally starts accepting movement commands. This guarantees that your hardware initializes safely, gracefully, every single time.
Let's move to a quick summary and see how this all builds into a completely new landscape for robotics. Look at this massive shift in architecture. We move away from the dangerous single point of failure in the ROS Master straight into the decentralized peer-to-peer magic of DDS in ROS2. We go from absolutely zero real-time guarantees to a robust system that supports strict deterministic latency, meaning you can finally trust it for life-or-death things like drone flight and autonomous braking. And we go from being trapped solely on Linux to having native support across Linux, Windows, and macOS. This single-handedly opens up modern robotics to a vastly wider pool of developers and industrial systems around the world.
So to wrap this all up, the transition from ROS1 to ROS2 wasn't just some simple software update. It was literally the entire field of robotics graduating from the safe confines of the research lab and stepping out into the real, unpredictable, high-stakes world. With decentralized communication, ironclad security, and true real-time capabilities, the glaring limitations of the past have finally been stripped away. The tools available to you today are more powerful and way more accessible than they have ever been in history. So I'll leave you with this one final thought. Now that ROS2 is the definitive standard, what intelligent machines will you build for the real world? Thank you so much for joining me on this explainer, and keep exploring.